Good afternoon, students. Welcome to the class. Today on cryptography and network security, we are going to deal about digital signatures. Today, we can explore the various concepts of digital signatures, which is a key topic in cryptography and network security. Digital signatures play a vital role in ensuring authenticity, integrity, and non-repudiation in digital communication. Let us go step by step and understand how they work, their properties. First, we can see about what is digital signatures. As you know, simple message authentication alone cannot always handle the issue of trust between communicating parties. Digital signatures address this challenge. They allow us to verify the author of the message, confirm the date and time of the signing, and ensure that the message contents have not been tampered with. Furthermore, they can be verified by third parties, making them useful for dispute resolution. In other words, digital signatures combine authentication with additional trust and security features. For a digital signature to be effective, it must satisfy several important properties. First, it must depend directly on message being signed, and it must use information unique to the sender. So forgery is prevented. It should be easy to produce for the sender and easy to verify for the receiver. At the same time, it must be computationally infeasible for anyone to forge it. Lastly, it must be practical to store the digital signature for future reference. These properties together make digital signatures trustworthy in practice. So let's see what is direct digital signatures. So in direct digital signatures, only the sender and receiver are involved. The sender signs either the entire message or its hash using its private key. Optionally, the result may also be encrypted using the receiver's public key. It is assumed that the receiver already has access to the sender's public key. An important detail is that the signature should be applied before encryption. The security of this scheme depends heavily on the sender's private key. If the private key is compromised, the entire security of the signature is lost. To handle such risk, timestamps and key revocation mechanisms are often necessary. So let's see what is digital signature standard. In early 1990s, the US National Security Agency developed the digital signature standard, commonly known as DSS. The DSS uses the digital signature algorithm, or DSA, along with the SHA hash function. Unlike RSA, DSS was designed purely for digital signatures and not for encryption. DSS produces a 320-bit signature while offering security equivalent to 512 2024-bit keys. The security of DSS is based on the mathematical difficulty of solving discrete logarithm problems, which makes it resistant to attacks. Now let's look on to how DSA keys are generated. First, global public parameters are selected. These include large prime numbers P and Q and the base value G. Each user then selects a private key, which is a random number less than Q. From this private key, the public key is derived using modular exponentiation. These keys, along with the global parameters, are then used for signature creation and verification. Digital signature creation. Let's see on to how digital signatures are created. To sign a message using DSA, the sender generates a temporary random number K, which must be unique for each signature and destroy after use. The values R and S are then calculated using mathematical operations involving the message hash and the private key and the random number key. Final signature is represented as a pair of R and S, which is sent along with the original message. A very important thing is that refusing the same K can completely compromise security. So it must be managed carefully. So we can see about DSS signature signing process. So here the formula for signing is displayed. The value of R is derived using modular arithmetic, and S is calculated using the hash of the message. The private key and R together, they form the signature R, S. This process ensures that the signature is uniquely tied to both the message and the sender's private key. So now let's see on the DSA signature verification. When the receiver gets the message and the signature, they need to verify its validity. The verification process involves computing several values such as W, U1, and U2. And finally, V. If the computed value V equal to R from the signature, then the signature is valid. This process ensures that the message was signed by the client sender and that it has not been altered. The mathematical difficulty of discrete logarithms ensures that an attacker cannot easily forge valid signatures. DSS signing and verification illustrates. On the sender side, the message is first hashed, then combined with the random number key and the sender private key to produce the signature pair. On the receiver side, the message and signature are processed through verification formulas using the sender's public key. If the computed results match, the signature is accepted as valid. This two-press process forms the backbone of secure digital communication. So now let's see how the public key components and the keys are used. In DSS, there are several global parameters used by all participants, such as large prime numbers, the prime divisor, and the generator G. Each user then has their own private key, which is a random integer less than Q, and a public key derived from it. Additionally, each signature requires a fresh random per secret number K. The correct use and protection of these keys are critical for maintaining the security of the system. Let's take a look on the certificate authority and key management. So, the certificate authorities and key management, one of the biggest challenge in public key system is the secure distribution of keys. Certificate authorities or CAs plays an important role here by issuing digital certificates that binds public key to user identities. These certificates help users verify each other's public keys securely. Additionally, public key encryption can be also used to distribute secret session keys for symmetric encryption. Together, CAs and proper key management practices ensure the overall trustworthiness of digital signature system.